During this video, we're going to be studying kinematics in 2 dimensions for Chapter 3. In our first example, we're going to look at a spaceship out in space. There's no gravity acting, so we don't have to worry about its weight, but we have these 2 rockets shooting firing to shoot the spaceship. One's an X rocket, one's a Y rocket. And when both of these fire, it can follow a path like this blue line here. It starts off with initial velocity in the y direction and initial velocity in the x direction, and ends up with a final velocity in the x and a final velocity in the y. The way we handle these types of problems is that we break them up into their x, y components. In other words, we look at only what's going on here in the x direction and only what's going on here in the y direction. We keep them separate. We don't look at any variables in the x along with the y. We look at the x direction by itself, and we look at the y direction by itself. So we really have 2 problems at once. There's 2 kinematic problems in one motion. The 2-dimensional motion of the spacecraft can be viewed as the combination of these separate x and y motions. So now we're going to look at how to handle such a problem. And in this particular problem, we have in the x direction, the spacecraft in figure 3.5 has an initial velocity component of 22 meters per second, and an acceleration component of 24 meters per second squared. In the y direction, the analogous quantities are 14 meters per second initially in the y direction, and the acceleration in the y direction is positive 12 meters per second squared. The directions to the right and upward have been chosen as the positive directions. What we want to do is find the displacement in the x direction and the final velocity in the x direction, part A, and then part B says to find the displacement in the y direction, the velocity in the y direction, and we're going to do this at a time after that occurs for 7 seconds. And then finally, we want to find the final velocity, magnitude and direction of that spacecraft, and again, that's after 7 seconds. So what we're going to do is look in the x direction first. The motion in the x direction is just a straight line with some kind of acceleration here. We're going to look at our given values in the x direction. Our initial velocity is 22 meters per second. Our time is 7 seconds. The acceleration in the x direction is 24 meters per second squared. We want to find the displacement and that final velocity. So now we have enough information to find out the displacement in the x direction by using x equals v of t equals 1 half at squared. Plug in our values, and we end up with an answer of a displacement of 740 meters. Now we're going to look at our final velocity in the x direction to decide what equation to use. And we'll use the v equals v0 plus at and plug in our values. And that gives us 190 meters per second. Now we're going to look at the y direction. We're going to list the given values. Oh, that's supposed to say y, not x right there. We're going to list the given values in the y direction. Initial velocity in the y direction is 14 meters per second. The time is 7 seconds. The time is one variable that can go back and forth between the x and the y. That's the only variable that can be shared between the 2 directions. Our acceleration in the y direction is 12 meters per second squared. We want to find the displacement in the y and the final velocity in the y. The motion we are looking at is just the y direction only. It's this upwards motion here. And we're going to use the exact same equations that we used in the x direction and plugging in all our values. You should pause the video now and try see if you can do that. Come up with 390 meters in the y direction and 98 meters per second as the final velocity in the y direction. Now we want to look at, we want to give the final velocity and find the direction. So we don't want x or y, we want a combination of the 2. In other words, we want the resultant velocity. So we look at the velocity in the x direction being 190 meters per second, velocity in the y direction being 98 meters per second, and we use the Pythagorean theorem to find that final velocity, which ends up being 210 meters per second. We also have to find that angle, so we're going to use inverse tangent to do that, and we end up with an answer of 27 degrees. Now we're going to look at a second type of problem that you have to know how to answer. And this is a 2-dimensional problem here on Earth. It's a projectile here on Earth. And so we have to, again, keep the x and y directions separate. So if you throw a rock and it follows a parabolic path, the x direction motion is totally separate from the y direction motion. The reason we can say that is because the, the only force that's acting on the object when it's in the air is its weight, and that weight is in the y direction only. There are no forces acting in the x direction to cause it to accelerate or decelerate because we're ignoring air resistance. So the only force acting on this object when it's in the air is in the y direction. So in all of these problems, projectile problems here on Earth, the acceleration in the x direction will always be 0, and the acceleration in the y direction will always be negative 9.8 meters per second squared. Today we'll be looking at horizontal projectiles only. This is a special case of projectiles. And what this means is the projectile is initially shot horizontally, and what this implies is that the initial velocity in the y direction is 0. There's no velocity in the y direction. It's not moving upwards, it's not moving downwards, it's perfectly horizontal. In projectile motion, the horizontal motion and the vertical motion are independent of each other. That is, neither motion affects the other. So a projectile only accelerates in the y direction. The acceleration in the x direction is 0. So if you're to drop a red ball here at the exact same time you were to shoot a yellow ball horizontally, what it will happen is they both start out with initial velocity of 0 in the y direction. Now this one, it does have the yellow ball has a velocity in the y direction, and that's why it has a distance off to the side. But if you look at the y direction, you'll notice that the heights of the red ball and the yellow ball are always the same at these various time periods. They fall at the exact same rate. So the red ball drops and the yellow ball is projected horizontally, and we notice that the distance the red ball and the yellow ball falls in the y direction is the same. And that's because they both start off with initial velocity in the y direction, and they both have the same acceleration in the y direction. They don't land in the same place, but they're in the air for the exact same amount of time. So what that means is that they will land on the ground at the same time. We have a problem here where it's a horizontal projectile, an airplane moving horizontally with a constant velocity of 115 meters per second and at an altitude of 1,050 meters. The directions to the right and upwards have been chosen as the positive directions. The plane releases a care package that falls to the ground along a curved trajectory. Ignoring air resistance, determine the time required for the package to hit the ground. And you'll notice there's a couple interesting things here. The care package is dropped, and so it has initial velocity in the x direction of 115 meters per second, and its velocity in the y direction is 0. And you'll notice that the velocity in the x direction stays the same. It's 115 meters per second the whole time. The airplane stays going 115 meters per second. So you'll notice that the airplane stays above the care package the whole time because they both are traveling 115 meters per second in the x direction. Now in the y direction, it starts off at 0, and you can see that the velocity in the y direction gets larger, and then it gets even larger. So we are accelerating in the y direction, but not accelerating in the x direction. So what this problem says is an airplane moving horizontally with a constant velocity of 115 meters per second and at an altitude of 1,050 meters. The directions to the right and upward have been chosen as the positive directions. The plane releases a care package that falls to the ground along a curved trajectory, ignoring air resistance to determine the time required for the package to hit the ground. So we're going to go ahead and realize that that the package is in the air for the exact same amount of time as if the package were to simply fall with no velocity in the x direction. So if you look at this picture here, A is the care package being dropped straight down, and B is the care package having a x velocity, but they both hit the ground at the exact same amount of time. So what you do is you just treat this problem as if it's just a free fall, just as if it's being dropped, and you find the time. So find the time to fall in the y direction. Our initial velocity in the y direction is 0 meters per second. Acceleration in the y direction, it should say negative 9.8 meters per second squared or negative 10 meters per second squared. The delta y is a negative 1,050 meters. The time is what we want to solve for. So we use our equation y equals VOT plus 1/2 AT squared. And we come up with an answer of 14.6 seconds after plugging all our values. The last question is question that says the Riddler drives his car off of a horizontal cliff that is 10 meters high at a speed of 25 meters per second. A policeman observes this event but realizes that the speed limit is 30 meters per second and he cannot give the Riddler a ticket. He decides to use physics to calculate what the speed of the car was in the air. If the final speed is over the speed limit, he'll give the Riddler a ticket. Holy gravity, Batman. So we're going to pause this, or I'm going to draw this picture and then go through this problem. So here we have our 10-meter picture. Here's the Riddler coming off the cliff at 25 meters per second. And what we want to do is find out what the velocity of the Riddler is down here at the bottom. And we know in the x direction, the Riddler is going 25 meters per second. But we have to find out what velocity in the y direction is so that we can then go ahead and use Pythagorean theorem to find out what that resultant velocity will be. So this is really a y direction problem. We're going to write all our values in the y direction. The initial velocity in the y is 0. The acceleration in the y is negative 10 meters per second squared. The change in displacement in the y is negative 10 meters. The the final velocity in the y direction is what I want to solve for. And looking at my variables, I realize I have to use the equation v squared equals vo squared plus 2ay. I plug in my values here and I get v squared equals vo that's 0 plus 2 times a is negative 10 meters per second squared. The delta y is negative 10 meters. And so now what we have to do is the velocity equals the square root of 200, which is 14.1 meters per second. So we go ahead and we have 14.1 meters per second right here. And now we have to do the Pythagorean theorem, a squared plus b squared equals c squared. And we plug in our values of our 14.1 meters per second, that's squared, plus 25 meters per second, and that's squared equals c squared. And so c ends up equaling 28.7 meters per second. So unfortunately, we cannot give the Riddler a speeding ticket. He only reached 28.7 meters per second while in the air and did not hit the speed limit of 30.